Welcome guys. So this is the new video list about the vector space and modules. Okay, so before I start, if you are interested, you can go to my channel list, and in the playlist, then you can check for the group theory lecture category. Okay, and yeah, so basically I have built a category theory and also a group theory and a ring theory. Okay, so I think the group theory and ring theory are somehow like a prerequisite to understand the vector space and modules. Okay, but I think you only need several of them. If you find that you don't understand some idea, then you can go into chat. Okay. Okay, so let's start. Okay, and I also want to say that I built all these video lists just for fun. Okay, so subscribe to my channel. Don't be serious. Okay, so the vector space, so all I intend to do is that we have group and ring theory, then we go to vector space and go to field, go to Galois, and go to homological. And once you have homological algebra, then you can study a lot of like algebraic topology and algebraic geometry. Okay, so linear algebra is somehow just a study of vector space. And some of the theorems are a little bit difficult, but I think it's still very simple. Yeah, so this video list should be very short. Okay. Yeah, so the reference is Hurston and Apostle. Yeah, you can check. I mean, there are a lot of linear algebra, but the textbook, most of them are almost the same. Also, quick definition of vectors: V is a non-empty subset, basically, and we over field F. So remember that we already say that field is basically commutative division ring. Or basically, with identity, every non-zero element has its inverse. So given a commutative ring with identity, and every non-zero element has an inverse, it's called ring. It's called field. Okay, so in general field, we use real numbers, rationals, or complex field. Okay. Yeah, but in our framework, then usually I think most of them we use a complex field, a complex field. Okay. Complex number. Okay, such that we have two operations. One is a plus, one is the scalar multiplication. So I use it. Maybe I somehow use times or basic. Yeah. So this is a scalar multiplication. Scalar multiplication. Okay, such that if alpha belongs to field F, and we get V and W belongs to V. And we have alpha V plus W is alpha V plus alpha W. And also alpha plus beta. So beta is also a field element. It's basically V, so alpha V plus beta V. And alpha beta V is alpha beta V. And 1V is V. Okay, so, and by the way, alpha V is basically in FV, right? So once you have all of these, then you call it a vector space. Okay. Over field F. So in the linear algebra, people seldom talk about this sentence, right? But by definition, you should to be rigorously, you should put it. Okay, so this is a very short axiom, right? If you see some textbook, they talk about a vector space use 10 axiom, but I only use 4. Okay. Okay, so yeah, so quickly says that in the original plus, this plus will make, so I should add another, is that I should add another axiom, is that you work in the V and only look at the plus is a abelian group. Right, so basically you are allowed to have zeros. So that means you have the zero vectors, and V plus 0 is a 0 plus V is a 0. Okay, so you focus on V plus is abelian group, and then for the field you add all these. Right, so this is the first axiom, the second set of axioms. So once you have these two, then it's usually agree. It's always agree with the common 10 axioms of the vector space. Okay, so yeah, basically we have abelian group and these 4 axioms. Okay, so now we just see the examples. Okay, so this is very trivial. Okay, so one example is that this is famous example is that you get a field and you contest another field, right? So you get a field K which cover F. So this is called a field extension. Okay, so common example is that Q is a real number is extension over Q, and a complex number is extension over R. Okay, so you have K and you take a subset such as subset is also field. This is field extension. So in this case that you can check K is a vector space over F. Okay. Yeah, this is somehow like different from your linear algebra, but the abstract algebra example. Okay, another example which is common. Suppose that F is a field, and then you define V to be alpha 1, alpha 2, up to alpha n, where all the alpha I belongs to F, field F, right? Then you can define a plus, right? You can define a plus. You get any two element, define a plus, just divide as a alpha plus beta, alpha 1 plus beta 1, alpha 2 plus beta 2, alpha 1 plus beta n. And then for each, you take any element in the field F, alpha I belongs to F, and take any element belongs to V. So let's say alpha 1, alpha 2, alpha n, it becomes alpha, alpha 1, alpha, alpha 2, alpha, alpha n. Okay. So check out this is a field. Check out this is a vector space. It's a vector space over F. Right. So basically, this is vector space. You're stupid, right? You order all the F into tuples, right? So this is general code isomorphic to Fn. Yeah. So this is a general notation. So this is the usual common vector space. So for example, in your common three-dimensional Euclidean space, this is called R3, right? Because your field is real numbers, right? So in your general n-dimensional real vector space, you are talking about Rn, right? So just take any field and multiple n. So this is the usual construction. You take any field and do the tuples of it. Okay. And if you like the quantum mechanics, people like to talk about Hilbert space. So Hilbert space is a complex vector space with some dimension to n. Okay. So this is the most common sense of the vector space. Okay. Which should be viewed as the same as this one if you learn a lot of math. Okay. Okay, another one. You can let V to be F bracket X. Right, so this is the polynomial ring over F. Right, so basically these are just A0, A1X, AN, XN, and all the AI belongs to field F. Okay, so yeah, so check out for example, check out V of X is a vector space over F. Okay, the easy for the addition just the usual addition, right? Take two polynomials, you know how to addition, and the scalar multiplication just times F in test any element into A0, right? So you can take. Okay, so yeah, easy exercise. Okay, and there's a subset. If you take Vn to be all the degree, all the polynomial degree less than n, then this Vn, basically this is a Vn is a subset of the F bracket X, right? So this is Vn is also a vector space. It's also a vector space. Okay, because the two polynomial with degree less than n, addition is still less than n, and tangent multiplication is still less than n. Okay, so now we can define a subspace. So subspace W is a subset of V such that W is also a vector space, Okay, so simple idea is that you can show that this is if and only if you take any two element in a vector space W, subset of V W, and then you check that where their addition is. Okay, and also And also you check that whether for all the alpha belongs to your field F, and for W1 belongs to W, your alpha W1 still in W. So once these two have proof, then you are guaranteed that this is a subspace. Okay, and this is the stupid exercise that you should check. Okay. Okay, the next is basically linear transformation. Okay, so give a linear transformation from V to W. So there are vector space V and W are collinear transformation such that T V1 plus V2 is basically T V1 plus T V2. And also T alpha V1 is basically alpha T V1. Okay, so once you set it for all V1, V2 belongs to V, and all the alpha belongs to field. Once you satisfy these two are called linear transformation. Okay. Yeah. So let me quickly define some notation. So if T is 1-to-1, then usually we call T is injective. Injective. Okay, so if T is onto, usually people talk about using the surjective. If T is both 1-1 and onto, and we say T is isomorphism. So if two vector space, if there is a T such that V from W, which is isomorphism, then usually we write V as the same as W. So it means that abstractly they are the same vector space. Okay, and also we should define kernel T such that all the element in the V such that Tx is 0. Okay, so this is, or sometimes I'm very lazy, so I just Tx is 0. Okay, so kernel T, and then your homework is to show that this is a subspace of V. Okay, and then you could design image. So basically it's a Tx such that X in V. So you ask about image, so this is also subspace of W. Okay. And then you can also define the harm. Okay, so harm of VW are all the linear transformations. So all the linear transformation from V to W. So the whole total is called homomorphism. Okay, but sometimes people like to talk about harm. So harm VW means that all the linear transformation from V to W. Okay. Okay, so lemma. So this lemma is simple. So if V is a vector space, then over field, and you get alpha 0, 0 for alpha belongs to field, and alpha 0, V 0 for all the V belongs to V. So basically anything times 0 is 0, okay? And then minus alpha V is minus alpha V. And if V is non-zero, then alpha V 0 implies that alpha is 0. Okay, so these are four easy lemma. Okay, so let me just prove some of them. So this one is basically trivial, right? Because alpha 0 plus alpha 0 is basically alpha 0 plus 0 by axiom is basically alpha 0, right? So alpha 0 is 0 because alpha 0 is alpha 0 plus alpha 0. Okay, and this one is also the same reason, right? Because 0 plus 0 V is 0 V, right? So which you get 2 0 V is the same as 0 V, so 0 V is 0. Okay, so the third one, check by yourself. The first one, let's maybe check the number 4. Okay, so number 4, if alpha V is 0, then alpha, and also alpha is non-zero, right? By the ring, right? Sorry, V is non-zero. By your ring, let me see. Okay, so let's see. So if alpha V is 0 and V is non-zero, so let's say suppose alpha is non-zero, right? Let the alpha inverse exists, right? Because this is a field, so you can tie something. So you get alpha inverse alpha V is V, but V is non-zero. Okay, and then this is 0. So contradiction with the number 1. So alpha must be 0. Okay. Okay, so let's define a quotient space. Okay, so quotient space should be easy, right? So if W is a subspace of V, then why it is easy, right? Because now we have the abelian group, so we can talk about quotient abelian group. So we can define a V quotient W, just X plus W for X belongs to V. Okay, and then there are isomorphism if the equivalent class is that if X and Y, sorry, if X and Y belongs to V over W and they are the same class, if and only if X minus Y inside is in the W. Okay, so you should view this as a quotient as abelian group. Okay, and the multiplication is also simple, right? Multiplication just times X, right? So alpha times X plus V. So X plus W is just alpha X plus W. Okay, so this is also a vector space. Yeah, so this is called a quotient space. Okay. And yeah, so also V1 plus W plus V2 plus W is basically V1 plus V2 plus W. Okay, so this is addition, this is the multiplication. Okay, so V over W is called a quotient space. Quotient space of V by W. Okay. So this is the powerful technique in the proof. So usually in the linear, if you're the freshman, you usually will not talk about quotient space. So in order to prove something, you need to do some trick, right? But once you know this abelian group and then you know the quotient space, this idea, then you can prove a lot of things very easy. Okay. Okay. So let's see. Oh. Okay. So let's see the definition. If V is a vector space over V over F, and U1, U2 up to UN, these are all the subspace of V. So be all the subspace of V. And as we say that V is called internal. Okay, so stupid name. Internal direct sum. Internal direct sum of U1, U2, UN means that for every element V belongs to V, then there exists U1, U2, UN. So this small U1 fall into a larger U1, such that V is the same as U1 plus U2 up to UN. And yeah, so U small UI, large UI. Okay, so yeah, so so this example, this idea means that given a vector space, given any element V, you can write as a linear combination of each subspace. Okay, so one idea is that in the 3-dimension, right, you write any vector in R3, then you can decompose into X, Y, and Z. So you can stack U1 as the vector space span of the x-axis, span of y-axis, span of z vector, and the R3 can decompose. Yeah, this is the idea of basis, and we will talk next time. Okay, but in this video we just call it internal direct sum. Okay, so yeah. Okay, yeah, yeah, this is called the internal direct sum. If any v is oh, I forget about there's another condition. Yeah, another condition that we hope this way, and this is the only one way. So the internal direct sum need to have another conditions that this is the only one way. So you cannot. So there's only one expression such that this will work. Right? You cannot find another U1 prime, U2 prime, UN prime such that their sum is the same. Okay. Okay. So so given any finite number of vector space over V, over F, right? Such that you have V1, V2. So now V up to Vn, it's just, yeah, basically they are all vector space over F. And I want to construct another vector space, which is called V. Basically, each element, let's say use a small v1, small v2 up to small vn, and basically all of vi's belongs to vi. And then the same, you can define addition and the multiplication, right? So addition is just the same, just add each coordinates times any variable, and for the scalar multiplication, just times any alpha into this. Okay, so this V will be a vector space, right? By definition. So usually this people write as this. Okay, so this is usually called external direct sum. Okay, so this V is just called usually called external direct sum of this V1 up to V2 up to Vn. Okay, so theorem. So the final theorem, if V is the internal direct sum. So V is the internal direct sum of U1, U2 up to UN. And I think you guess what I'm saying, right? If V is the internal direct sum of U1 up to UN, then V is isomorphic. So basically, we should view as an abstract semi-vector space isomorphic to the external direct sum. Of U1, U2 up to UN. Okay, so what I'm saying is that the first two definition, one is called internal direct sum, and the external direct sum is actually the same. So we need to, I think this is very intuitive, right? But what let's prove. Okay, so suppose V belongs to V, and now this V should be uniquely written as the one way, right? Uniquely written as a V1, sorry, U1, U2 up to UN, right? Which all UI belongs to U, right? So now I can define a map from T to define map T to V into what? Into the, right? So by definition, right, this V can be uniquely written as U1 plus U2 UN, right? So I can map this to U1, U2 up to UN, right? So I can define a linear map from V to U1, U2, UN, right? So this is the external sum, right? There is a linear map such that the T of V just map into each coordinate. Okay, so we need to prove it's isomorphic, right? So what I want to basically, you just need to show that T is isomorphic. Okay, so you need to check T is linear, and the T is 1, 1, and the third is T is onto. Okay, by definition, for any V, right, you can write it as this way, right? So by any V, right, by any V, you can write it all this way, right? So onto is trivial, right? Because I mean, oh sorry. So onto means that you pick this one. You pick any U1 up to UN. There's a V which map into it. And by definition, if you pick out U1, U2 up to UN, then you just define V to be sum of this, right? So the T is onto is a trivial one, okay? And then T is 1, 1. T is 1, 1 means that different V should give you different U, right? But by definition, this is the only way. By definition, my internal direct sum defined the only way, right? So different V must have different U. So at least one component should be different, right? So T is 1, 1 is also trivial. Okay, and the T is linear is basically from definition, right? You can check by yourself. If V1 is obvious, stupid, right? If V1 is just U11, U12, U1n, and the V2 is U21, U22, up to U2n. The V1 plus V2 just U11 plus U21 plus U12 plus U22. But the U11 plus U21 is must fall into the U1, right? Because U1 are vector space, right? So T is linear. Okay, so check by yourself that yeah, I already checked. Yeah, so yeah, so very simple. Yeah, so next time we talk about basis, and maybe we prove the the rank numerality theorem. And yeah, this is an interesting topic because the linear algebra somehow contains very lots of the intuitive idea, right? Like the numerality theorem, diagonalization, Jordan form, right? But the actually most of them are very non-trivial. And sometimes you need to use the algebraic structure of your field, right? So for example, if you want to solve the eigenvalues, you must prove that you must need to use your use the idea that every non-zero polynomial in the complex field usually has always have the roots, right? So linear algebra is people think linear algebra is simple, but linear algebra is very interesting and not so simple. Okay, see you guys next videos. Bye bye.